All right, good morning, AP students, or good afternoon, depending on when you're watching this. Welcome to your AP problem walkthrough on atomic structure, isotopes, and photoelectron spectroscopy. So what we're going to look at is, of course, we're going to start off with a couple conceptual questions, and then I will put in the description the time when the AP problem starts. And those will be the types of problems that I check for completion. So let's go ahead and get on it. So what we have here is question number 39 on page 10. We are given a photoelectron spectrum, and what we see here is it's graphed against binding energy. So instead of starting at 0 on the left, we actually see that we start at 0 on the right. So make sure you're reading the graph correctly or the spectrum correctly. And what we have here is we're being asked to interpret this according to the following questions. What is the element likely being represented? Draw a Bohr model for this element, write the electron configuration, and then we'll do a little bit of math. So first and foremost, remember that photoelectron spectroscopy is essentially a visual of the electron configuration of a given atom. So that means we're always able to identify an element. So this is an instrument or analytical tool that we use to identify elements present. What happens is we shoot a bunch of energy and we see how much energy is required to break off an electron. And depending on that electron's location, a certain amount of energy creates a certain amount of peaks. Also, depending on the amount of electrons in that location, specifically that orbital, right? Not specific location, because that's unique, right? Pauli exclusion principle, but the general orbital energy level area, we can also identify how many electrons are present, depending on the amount of energy, the multiple of energy that we were needing to create the ejection of an electron. So using the PES spectrum below, answer the following. So what element is this likely being represented? Well, the closer you are to the nucleus, you are going to have a higher binding energy because it's going to take more energy to remove you from, to eject you from that energy level because you're stable. You're really close to the nucleus. You're where you want to be. You're at your ground state, right? So the first peak in general is always 1s, energy level 1, orbital s, okay? And what you'll see here is we get a ratio. We get a ratio on the x-axis as each line represents 1. So we have 1s2, and it's completely full. And we know it has to be full, by the way, because we see other peaks. We can't half fill one level and move on, okay? Because right now we're graphing or we're determining the ground state configuration of an element. And so then what we do is we move on. Well, what we're noticing is a huge binding energy difference between energy level 1, S2, and energy level 2, S2. Okay. And this makes logical sense because you can't really, there's no other 1S. There's like no 1P, there's no 1D, so you have to move on to the second level. So this becomes 2S2. How did I know that it was 2? Well, if you look at the height ratio, it's the same ratio as the initial 1S, and 1S was completely full when it hit the 2 line. So then we move on to 2P. Okay, now we need to pay attention to the ratio, but the little cheat is that you see that there's still another peak afterwards. So you know that this is a full 2p6. You can also count the lines. It goes up to line number 6. And if we're looking at each line as a 1-to-1 ratio, then you're seeing that we have 6 lines surpassed. So we're going to be at a 6 electron count. And then the last one is moving on, 3s. Okay, and notice it hits the second line, so 3s2. And if you just say to yourself, oh, wait a second, why isn't it 2pd? Well, we don't have a 2pd, so that's why we have to move on to the next available orbital, which is in the next energy level, row 3. So what we have is our constructed electron configuration, so that means we can actually just answer C right away, that this is going to be 1s2, 2s2, 2p6, 3s2. Okay, our ground state configuration based on our photoelectron spectroscopy or spectrum. So what is this element representing? Not just likely, I really should remove that word. It is representing 1s2, 2s2, 2p6, 3s2, that would be magnesium. Okay. So these are great questions. They're very common on FRQs as part of an FRQ, and they're very common as MCQs. So go ahead and draw a Bohr model in the space to the right. So remember, Bohr models are really valuable mainly for the reason that they offer a depiction of the electron arrangement based off of energy level. They are not up to date in terms of the quantum model, right? The quantum model is far more specific. But if we also, by the way, if we want to be super accurate, what we actually see is that as you go up in energy level, the distance between the relative energy levels decreases. So that's why we see such a mega jump between 1s2 and 2s2, and a smaller jump between energy level 2 peaks and energy level 3 peaks. So just a little side note, that yeah, your energy levels as you go up them in an atom, you actually notice that the difference in energy between them, the difference in discrete energy between them, is smaller and smaller. So that's just like a little side note. And what I would do here is I would say in 1s2 or energy level 1, I have 2 electrons, okay? And according to the quantum mechanical model, they reside in the s spherical orbital. But the Bohr model is 2D. It's very flat. It's just graphing the general location. Then for we still have 2s2 and 2p6, which means we have a total count of 8 electrons in the energy level 2, filling up the entire row on the periodic table and the entire ring on the Bohr model and the entire energy level in the quantum mechanical model. And then we have in the third 2 electrons. So I'm going to put them up here. And that would be our Bohr model, again, which is a very old model, but we do like it, and you should know how to read it simply because it actually reveals a really important subsect of electrons known as valence electrons, which are really important for understanding bonding. And then finally, we have the question, if a series of photons with a wavelength of 560 nanometers bombarded this element. So this is the kind of the energy that we shoot it with, the energy particles we shoot it with. Would any electrons eject? So hint, calculate the energy and then convert joules to megajoules, because our graph is in megajoules per mole. The binding energy is also equivalent to the energy that's required to eject an electron, and then examine the spectrum. So let's calculate the general energy that a 560 nanometer photon would create. So energy equals Planck's constant times speed of light all over frequency, or sorry, wavelength. Why did I say frequency? Wavelength. And what we get is this is equal to 6.626 Planck's constant times 10 to the negative 4 joules per second times the speed of light, 3.00 times 10 to the 8th meters per second, which by the way can sometimes be written as like 2.998. Just use whatever constant that the AP equation gives you on the sheet for the exam. Okay. All over the why do I keep on saying frequency? The wavelength of nanometers, but we're going to convert nanometers into meters in order for our units to be compatible in this equation, because we want to cancel out meters and seconds and we want to just be left in joules. So we're going to turn this into 560 times 10 to the negative 9th meters, which is equivalent to 560 nanometers. And we get that we have an energy that we're shooting at this element with of, let's say, 3.5496 times 10 to the negative 19 joules. Now, our graph is in megajoules, so let's go ahead and take that next step so we can do an accurate comparison. Let's say that 3.5496 times 10 to the negative 19 joules is going to be equal to, for every 1 megajoule, you have 1 times 10 to the 6 joules, and that's going to give you a energy value in megajoules of 3.55 times 10 to the negative 13th megajoules. And I believe that is to the correct sig figs. Ooh, actually, it should be a 2 sig fig. So that would be 3.6. Okay, times 10 to the negative 13th megajoules. So when you look at our spectrum, we say, well, is there any value that is to the negative 13th megajoules that would still result in an electron being ejected? And what we're seeing is that the only read we have for a low energy requirement to eject is 0.74 megajoules. But we're still in the negative 13th power of 10. So we're going to say no electron would be ejected. Because based off of our spectrum, we'd have to have at least 0.74 megajoules to even get the outer electrons, the valence electrons in energy level 3, orbital S, okay, and 2 of them to eject, right? Or even 1 of the 2 to eject. So, excellent work. That's your first conceptual. Let's move on. I think we have one more conceptual to walk through. Or it looks like we're just hopping straight into the AP questions. Sometimes I forget which problems I choose. We're going to go to question 2, short FRQ. Again, these are about 4 points, and the AP allots about 9 minutes. We did part D, okay, and we're going to move on to part A, which is electron configuration. So write the electron configuration for the valence electrons. Your valence electrons at the ground state are your outer most electrons, or another way to think about is the electrons in the highest energy level or the highest principal quantum number, right? So what we see here is for livermorium, all right? The entire electron configuration would take you a while to write because livermorium is in row 7. So what we're going to do is we're just going to focus on writing the part of the electron configuration that focuses on row 7 electron location. So for livermorium, we would say that the electron configuration is 7s2 because livermorium, to get to livermorium, you do fill row 7 s orbital, and there must be 2 to be full. And then we go on to 7p4. And that is a question that you might be asking yourself right now is, wait, wouldn't I go to 5F, 6D, and then 7P according to electron configuration? And your answer is absolutely yes, except for the fact that I asked for valence electron configuration, which means I'm only focusing on the highest energy level. So now I'm ignoring the relative energy levels of orbitals, where we see that shift down in D and that 2 energy level shift down in F blocks. And I'm just focusing on the highest energy level valence electron configuration, which is going to be highest energy level 7. So I'm only going to focus on that. So 7s2, 7p4. All right, so that's it. And then we're going to move on to question short FRQ 5. So here we have a photoelectron spectroscopy for an unknown element, and we are asked to identify the unknown element and write its electron configuration based on the PES, and that's the shorthand. And then we're asked to consider the element in the periodic table, and we're actually going to hold off on part B because it's going to be reliant on your understanding of periodic table trends. So we're just going to focus on part A today. Okay. So based on the photoelectron spectrum, identify the unknown element. Again, what you're looking at here is the closer the electron is to the nucleus, the higher the binding energy, which is why we see us decreasing as we go along the x-axis, a very reverse way of thinking. We are in megajoules per mole, but since we're not doing any calculations, that doesn't matter as much. And what we see here is immediately 1s2. How did I know that it was 1s2? Well, we usually start there because if we're talking about ground state configuration, right, you can't jump to level 2 until you filled level 1. 2s2. How do I know it's full? Well, I could look at the ratio between the first peak and the second peak, or I can notice that there's still a peak afterwards, which means I've definitely filled the next orbital. 2p6, 3s2, And now I need to pay attention to my ratios in order to determine the height and what that means about the amount of electrons present. 3p, 1, 2, 3. So my electron configuration is 1s2, 2s2, 2p6, 3s2, 3p3, giving me the identification of the element as phosphorus, or P. All right. So really good job, you guys. That's all I have for you. Be prepared to have a homework check on this. And don't forget, if you are not prepared that day, you can always submit in Canvas later proof that you did this. So good work, you guys. Best of luck.